in this final lecture on magnetostatics, I am going to solve some problems on calculating vector potential, calculating the current distribution corresponding to a vector potential, and so on. So, this is a lecture on problems in magnetostatics, and from next lecture onwards I will do for some lectures the time dependent phenomena and start with Faraday's law. So, first problem that I am doing is from Zangwill's book. And this is problem 11.1. And it says that a current distribution produces the vector potential A r theta phi, and I need not say when I am using r theta phi, I am using spherical polar coordinates equal to phi unit vector mu naught over 4 pi A naught sin theta over r e raised to minus lambda r. Then what we want to know is what is the magnetic moment associated with this current distribution. So, this problem is quite straightforward. I want to calculate J r, and once I know J r, the magnetic moment associated with this will be given as 1/2 integral dV r cross J r. And how do I calculate J r? J r is related to the Laplacian of the vector potential. So, I get del square A vector potential equals minus mu naught J r, and I have been given A. A is given to be phi mu naught over pi. Let me also put A naught here, these are all constants, sin theta over r e raised to minus lambda r, and I want to calculate its Laplacian. Notice here that the unit vector phi is not a constant unit vector. So, I have to take the Laplacian of this also. A better approach would be to write phi in terms of constant unit vectors, and I will do it in terms of x and y. So, phi is sin phi x plus cosine phi y, and x and y are constants. Then I can just focus on only the function part and not worry about differentiating the unit vector part. So, I can therefore write the vector potential A as phi mu naught A naught over 4 pi sin theta over r e raised to minus lambda r, which I can write as minus x unit vector mu naught A naught over 4 pi sin theta sin phi over r e raised to minus lambda r plus y mu naught A naught over 4 pi sin theta cosine phi over r e raised to minus lambda r. At this point, I would also direct you to a problem in Griffiths. So, this is problem 24 of Griffiths' book, chapter on magnetostatics, where he wants you to find J for vector potential A equals k phi. So, if you play with this problem, you will see exactly what I am doing here. So, now finding J is very easy. I will write J r is equal to minus 1 over mu 0 del square of A, which in our case then will become minus 1 over mu 0. In the x direction, I will have del square of sin theta sin phi over r e raised to minus lambda r, and in the y direction, I will have del square of sin theta cosine phi over r e raised to minus lambda r multiplied by mu 0 A 0 over 4 pi. So, I get J r equals minus A 0 over 4 pi and this whole thing, x and y and rest of the expressions. And after this, the magnetic moment of the current distribution will be given as 1/2 integral over the entire volume r cross J r. I leave the rest of the problem for you. Let us go to the next problem. Which I am again taking from Zangwill's book. It is not exactly what is given in that problem, but related to Zangwill's problem 11.3. And the problem is as follows: a cylindrical tightly wound solenoid has length L and radius r, let r be much less than L. It has n turns per unit length and carries current I. Calculate the magnetic field outside the solenoid in the plane bisecting it. At a distance s from its axis. And you are given that s is much greater than r. So, what this problem is asking you is to, there is a solenoid of radius r, a long one. I am looking at the bisecting plane of this solenoid. Its length is L. So, let us take this plane to be the xy plane or z equals 0 plane. In the bracket I will write this is x y plane. It carries current I in these tightly wound wires. So, this is along the z axis. I want to find the field at a point P, which is at a distance s from its axis. The radius of the solenoid is r and its length is L. So, lower side is L by 2, the upper side is also L by 2. So, this is the calculation that I want to do. Since it is given that S is much greater than R, I can take the solenoid turns to be forming a dipole. And then what I will do is calculate the field using the dipole formula and then integrate it. So, let us see what I plan to do. I am going to take at height z a section and treat this as a dipole. Since the current is going as shown, this is going to be dipole in the positive z direction and its magnitude is going to be d m, because I am going to take the thickness of this section to be d z. Calculate the field due to this dipole at point S and integrate. So, I hope the idea is clear. What I am doing is I am calculating d b due to this dipole, which is going to be mu 0 over 4 pi 3 d m dot r unit vector r minus d m over r cubed, where r is the distance from this dipole to the point P, and to calculate B I will integrate this from minus L by 2 to L by 2. This is the variation of z. So, I hope the plan of how I wish to calculate this magnetic field is clear. So, let us now proceed with the calculation. So, here is this solenoid and I am not showing anything else except that this is z equals 0 plane, and I am at a point P. I have taken a section of this solenoid at height z, and the height of this section is dz. So, dm for this section is going to be n I pi r square dz in the z direction. R vector from dm to P is equal to S minus z. And as you can see, I am using cylindrical coordinates. So, I can write now dm at this point as mu 0 over 4 pi n I pi r square that I am taking from dm times 3 dz z dot s unit vector minus z unit vector times s minus z minus m dm, which is nothing but dz z, but I am going to divide by the power 5. So, I am going to multiply this by s square by z square divided by s square plus z square raised to 5 by 2. It is supposed to be 3 by 2 if I use unit vectors in the first term. So, here is dB, not dm, dB. So, let us correct this. This is dB. All I have to do now is integrate it. So, I can write B as mu 0 n I over 4 r square. I have cancelled this pi, and inside I am going to get 3 z dot whatever quantity I have written is going to be minus z times s minus z unit vector, that is the first term, minus z s square plus z square, that is the second term, divided by s square plus z square raised to 5 by 2, and I am integrating this from minus L by 2 to L by 2 over z. Simplify this. This comes out to be minus L by 2 to L by 2. This constant term mu naught n I r square by 4, and inside I get 2 z square minus s square in the z direction minus 3 s z in the s direction divided by s square plus z square raised to 5 by 2 integrated over dz. That is my answer for B. Notice that integration minus L by 2 to L by 2 3 s z over z square plus s square raised to 5 by 2 dz is 0, because the integrand is odd in z. So, I am left with only one term. So, I get b is equal to, it is in the z direction, mu naught n I r square by 4. Then I have this integral minus L by 2 to L by 2 to z square minus s square over z square plus s square raised to 5 by 2 dz. Integral I need to perform. Since this is an even integral, I can write this as z mu naught n I r square by 4 times 2 integral from 0 to L by 2 and the rest. So, this comes out to be z mu naught n I r square by 2 integral 0 to L by 2 to z square minus s square divided by s square plus z square raised to 5 by 2 dz. And this is a very simple integral to perform. I am going to take z equals s tangent of theta, so that dz becomes s secant square theta d theta, and b therefore, at s z equals 0 comes out to be in the z direction mu naught n I r square by 2 integral 0 to tan inverse L over 2 s inside I get 2 tan square theta minus 1 s square s secant square theta d theta divided by s raised to 5 secant 5 theta. This integral is quite easy to evaluate. So, let me just focus on theta integral. This s square and s give me s square here. So, this becomes in the z direction mu naught n I r square over 2 s square 0 to tan inverse L over 2 s. You simplify this secant square and all that, and you end up getting 2 tan square theta minus 1 cosine cube theta d theta. And I will right now focus only on this integral. So, this integral is 0 to tan inverse L over 2 s. I can take cosine square theta inside and write this as 2 sin square theta minus cosine square theta cos theta d theta, which is then equal to 0 to tan inverse L over 2 s 3 sin square theta minus 1 d sin theta. So, we have simplified this integral, and this is integral 0 to tan inverse L over 2 s 3 sin square theta minus 1 d sin theta. Take sin theta to be x, then this integral becomes 0 to value of x at L over 2 s is going to be L divided by square root of L square plus 4 s square 3 x square minus 1 dx. So, then the integral becomes quite simple. You do this integral and this will come out to be L cube over L square plus 4 s square raised to 3 by 2 minus L over L square plus 4 s square square root, which is nothing but L over L square plus 4 s square raised to 3 by 2. Inside I get L square minus L square minus 4 s square. L square term cancels and you get minus 4 L s square divided by L square plus 3 s square raised to 3 by 2. And therefore, the answer for B at s z equals 0 is z mu naught n I r square divided by 2 times minus 4 L, there was s square also, minus 4 L s square divided by L square plus 4 s square raised to 3 by 2. This s square cancels and you get the answer in the z direction, negative z direction, 2 mu naught n I. I will take r square out, L r square divided by L square plus 4 s square raised to 3 by 2. That is your answer. So, answer for B for this solenoid of length L is S z equals 0 equals minus z 2 mu naught n I L r square divided by L square plus 4 s square raised to 3 by 2. That is the answer. You may wonder where did I use that S is much greater than R. So, S much greater than R allowed me to make dipole approximation for each ring in the coil. Let us now look at some limits of this B. So, for this long solenoid of length L, radius or R or diameter 2 R, I have gotten the field in the mid plane as B at a distance S and z equals 0. So, this distance is S from the axis is equal to minus z 2 mu 0 n I L r square divided by L square plus 4 s square raised to 3 by 2. Let me take limit where L is much greater than S, which is greater than R. Then I can write this B as minus z 2 mu 0 n I L r square over L cubed. So, this goes as minus z 2 mu naught n I r over L square is proportional to 1 over L square. As L goes to infinity, this goes to 0, as we well know, for infinitely long solenoid, field outside is 0. Limit 2, limit S tending to infinity, S much greater than L and tending to infinity. Then I will have B S z equals 0 is equal to minus z 2 mu 0 n I L r square over 8 s cubed. Which is of the form m over r cubed. Let me show you how. For this long solenoid, when I am really far away, it looks very small. So, I will cut this and it becomes like a small magnet of magnetic moment m, where m would be equal to pi r square n L I in the z direction. And the field in the plane of the magnet perpendicular to m is going to be equal to mu 0 over 4 pi minus m over s cubed, and that is precisely what this is, except I was missing a mu 0 over 4 pi here. This I will leave for you to show. The problem is stated in the book in a slightly different way. They want you to use an argument to get this dependence of the field on L, and that I will give as an assignment. Next, problem 3. Again from Zangwill. And this is problem number 12.4 and concerns forces between two wires. So, it is an interesting problem and compares the forces between two wires, which are electrical as well as magnetic in nature. So, the problem says that two long parallel wires of length L each separated by distance d have cross sectional radius A is much less than d, and they are connected by U-turn at each end. To form a closed circuit. One end carries a battery of EMF V, and the other one a resistor of resistance R. Assume that R is much greater than the resistance of the wires. show that wires attract or repel depending on the value of R, and find that value. So, let me explain what the problem is. Here is the problem's statement. There are the two wires which are parallel, and of length L each, and on one side they are connected by a battery of voltage V, and on the other side there is a resistance R, so that there is a current flowing, and the current value I is going to be V over R. Now, there is going to be a potential difference between the wires of magnitude V, and this is going to be created by some linear charge lambda on the higher potential side and minus lambda on the lower potential side, like in a capacitor. The potential is going to be same throughout, because we have assumed that the resistance is almost negligible. So, there is no potential difference across these thick wires. All the potential difference is across this resistance V. So, because of this lambda, there is going to be attractive force between the wires, and they carry current in the opposite direction. So, there is going to be a repulsive force because of the magnetic field, and the two forces are going to compete. The lambda is not going to depend on R, because lambda depends only on the potential difference. So, the electric force is independent of lambda of R, whereas magnetic force is dependent on R because of the current I depending on R, and therefore, depending on R, either the electrical force will be larger than the magnetic force or smaller, and that is the R where the repulsion or attraction will switch from one to the other. So, let us do the calculation now. So, I have stated the physics of the problem. Now, I will just make these two wires a little thick. This distance d is supposed to be much larger than A, and therefore, I can take lambda to be as if it is on the axis, although there is no electric field inside the wires. So, the entire wire is on potential V here and 0 here if you like, and the potential difference arises when I move from one wire to the other. The upper wire carries charge lambda, lower one minus lambda. So, if I am at a distance y from the lower wire, the electric field is going to be lambda over 2 pi epsilon 0 y, and let us say the way I have made the charge is this is going to be attractive electric field here, and the other one is going to give me the repulsive electric field. So, that the two fields are added lambda over 2 pi epsilon 0 d minus y. That is the electric field in between the wires, and therefore, the potential difference V is going to be E dy we take care of the minus sign and all that, I will just write the answer. This has come out to be lambda over 2 pi epsilon 0 integration dy from a to d minus a. You see the distance is a here, and from here to here is d minus a. And the other term is going to give me plus lambda over 2 pi epsilon 0 integration a to d minus a of dy over d minus y, and the first one has y. You do the integration and the answer comes out to be that v is equal to lambda over 2 pi epsilon 0 log of d minus a over a times 2. Both the integrals give me the same answer, which is equal to lambda over pi epsilon 0 log of d minus a by a, which I can approximately write, neglecting a in comparison to d, as lambda over pi epsilon 0 log of d over a. And this gives me lambda in terms of v, which is equal to pi epsilon 0 v over log of d over a. And therefore, the electrostatic force, the electrostatic force per unit length between the two wires is going to be lambda over 2 pi epsilon 0 times lambda. So, this is lambda is square d, which is going to be pi square epsilon 0 square v square over 2 pi epsilon 0 log of d over a square times d. 1 pi cancels and you get the force to be equal to pi epsilon 0 v square over 2 epsilon 0 d log of d over a whole square. That is the electrostatic force. Now, I will calculate the magnetic force. Magnetic force per unit length by Ampere's law is equal to mu 0 I square over 2 pi d, which will be mu 0 over 2 pi d. I is nothing but v over r square. This is magnetic force. So, wires will repel if magnetic force is larger than the electrostatic force, which we have calculated to be pi epsilon 0 v square over 2 d log of d over a whole square, and that gives you a value of r, across which the nature of force will change from repulsive to attractive or attractive to repulsive, and this gives you r less than 1 over pi square root of mu 0 over epsilon 0 log of d over a. In that case, they will repel, otherwise they will attract. Next, problem 4, and this is related to a current distribution and the average of magnetic field over a sphere, and it gives a term which is related to m, the magnetic moment, with a delta function. That I will give in the problem in an assignment problem, but here I just want to show how that term arises, and that will lead to that delta function term. So, the problem is a current distribution J r gives rise to a magnetic field B r. If a sphere encloses the current distribution, then show that integral of B over the sphere is equal to 2/3 mu 0 m, where m is the magnetic dipole moment corresponding to this current distribution. This problem in the books is usually solved using all the mathematics, but I will show you an observation that will make this problem quite easy, and then you can relate this to other problems of similar kind. So, what you are given is a current distribution, and this is enclosed in a sphere. This current distribution gives rise to a field B r, and I want to calculate integral of B r dV over the sphere. Now, B r is going to be, by Biot-Savart law, mu 0 over 4 pi integration J r prime cross r minus r prime over r minus r prime cubed dV prime. J is a vector. So, when I want to calculate this integral B r dV, this is going to be mu 0 over 4 pi integration J r prime cross r minus r prime over r minus r prime cubed dV prime, and then I am integrating it over dV also. That is the answer. Now, what I will do is I will write this integral in the following manner: mu naught over 4 pi integral, I will write dV prime first, J r prime, and this is crossed with the other integral, which is dV of r minus r prime over r minus r prime cubed, and this is over the sphere. And now, we make that observation I was talking about. You see this term dV r minus r prime over r minus r prime cubed is related to the electric field of a uniform charge distribution over a sphere. How so? Suppose I am given a sphere carrying uniform charge rho, then the electric field at any point will be given as 1 over 4 pi epsilon 0 integration rho r prime r minus r prime over r minus r prime cubed d v prime. And we are saying that this is a uniform charge. So, rho r prime is a constant, and let us take this to be unity. Then E r is equal to 1 over 4 pi epsilon 0 integral r minus r prime over r minus r prime cubed d v prime. And this, by Gauss's law, I know is rho over 3 epsilon 0 r. So, this is going to be r over 3 epsilon 0 for r inside the sphere, and this is going to be equal to 1 over 4 pi epsilon 0 times 4 pi by 3 r cubed times 1, that is the total charge, 1 over r square r unit vector for mod r greater than r. Right now, since I am talking about J inside, I am just interested in what happens inside. So, what I am getting is, when I am given this charge distribution enclosed in a sphere, and I am calculating integration V r d v, it comes out to be mu 0 over 4 pi integration d v prime j r prime cross integration r minus r prime over r minus r prime cubed d v. And I have just told you that for r prime being inside, I have 1 over 4 pi epsilon 0 integration r minus r prime over r minus r prime d v prime is equal to rho r over 3 epsilon 0. I can cancel this epsilon 0, and I get 1 over 4 pi integration r minus r prime over r minus r prime d v prime equals rho r. Now, exchange r and r prime to get 1 over 4 pi integration r prime minus r over r prime minus r cubed d v equals rho r prime over 3. You see, we have gotten this integral along with this 4 pi. So, I can write b r d v integral equals mu naught integral d v prime j r prime cross rho is 1. So, minus r prime over 3. The minus sign comes because the way I have written the integrals is r prime minus r over r prime minus r cube d v, which is rho r prime by 3, and the integral I am interested in b d v is r minus r prime. This I can write as mu 0 over 3 integral d v prime r prime cross j r prime, and that takes care of the negative sign, which I can write as 2/3 mu 0 1/2 integral d v prime r prime cross j r prime, which is nothing but m. So, 2/3 mu naught m. So, I have shown if this current distribution is enclosed in a sphere, then the integral of B over that sphere comes out to be 2/3 mu naught m. Imagine now if I have a point dipole and I keep reducing the size of the sphere, even if it becomes of size 0, I will have this value to be finite, and therefore, I will pick up a delta function. I will give this as a problem. Related problems would be, if I am given this current distribution and I take a sphere outside, so this sphere is outside the current distribution. What will be the value of P r dV over the sphere? Another related problem is, given a charge distribution rho r prime, calculate the integral of E due to this charge distribution dV over a sphere in cases 1, when the sphere encloses the charge distribution, comma, and 2, when the charges are outside the sphere. I am leaving this problem for you. So, to conclude, we have solved some problems related to forces, fields, current distribution, vector potential, and magnetic dipole moment, and so on. These problems will help you solve the assignment problems and other similar problems in the future. Thank you.